because we don't even want to
Yeah,
consider
like if
walls.
I'll have that.
I think I'm recording. What are you saying? Double check. Yeah, the room's unmuted. I'll mute myself.
Okay.
Did anyone join or? Yeah. Okay. All right. I sent out a link. So, yeah. So today, just gonna go over some basic principles of aerodynamics. So we're just gonna start with some basic fluids concepts, and then just work our way through a little more about airfoils in particular, and then see how that applies to specifically race cars. So yeah. So starting out with fluids. So what is fluid mechanics? Pretty simple, right? So it's just the study of solids interacting with fluids, and in our case, we're just focusing on air. It's like regression of aerodynamics in Formula. You see the first use of aero on a Formula 1 car was the Lotus 49 back in '68. A lot has changed since then. That's McLaren, the newest McLaren, the latest race from this weekend. You guys saw that. It was pretty cool.
You did well.
Yeah, it did. It did do well. But yeah. So in general, why is it important? Pretty basic. Obviously, the more normal force you're having on your tires, the more tire traction you're going to have. You can tune the car to oversteer, understeer, neutral steer, and also direct airflow to particular locations on the cars. For example, maybe towards the duct, towards an air intake, et cetera, and also prioritizing the decrease of vehicle drag. So starting out, some basic terminology that just expect everybody to know here, like vectors, scalars, I mean, everybody should know that. What pressure is basically any force that's acting normal to an object. What density is, temperature, just like the measure of kinetic energy in a fluid or a solid. And then this is also another pretty important concept we should spend a little time looking at, the difference between streamlines, streak lines, and path lines. Have a little GIF there, but essentially streamlines are the dashed lines there. You can see that they are time dependent. So, I mean, everything is time dependent, but basically we can denote a velocity field by a bunch of streamlines. So if you imagine just like we snapshot a particular flow in one instant of time, what is each at each point in the flow, what is the direction of motion that flow is taking, essentially. And we can do that at every single location in whatever sort of like enclosure that we're looking at. So just in this two-dimensional flow example, we can sort of see like how time progresses. We can see how the streamlines and the velocity vector fields are changing correspondingly. And streak lines are a little bit kind of weird to kind of comprehend. But if you kind of just imagine like you release maybe some sort of die is like the common example at a certain point. So like essentially they're defined as all the particles which have passed through a particular loci. So if we imagine like the origin there as like that particular loci of which like this streak line is going through, then essentially if you just release like a bunch of die at that point, what is like sort of like what is that die going to look like as time progresses? And you can kind of see like it's kind of like a little bit difficult to understand like what exactly is happening there, but essentially as the velocity field is introducing more and more of a vertical component on this graph, we can sort of see how the entire curve of the streak line is sort of like shifting up with the that entire like die, and that entire curve is sort of like shifting up with that vertical velocity component, which is increasing as time goes on. So yeah, so I mean, obviously in this case, like the flow is accelerating, it's changing direction and changing magnitude with time. And then path line is pretty simple to understand. It's basically like the path that a single particle is taking. So you can sort of like, if you trace like a single particle, so the streak lines, remember that's not a single particle, that's like a bunch of different particles which have passed through like a particular loci, and like how that sort of like changes with time. But like a path line is sort of just one single particle. What is that path that it's sort of taking? Does everybody sort of understand that? It took me a while to sort of like understand like what the hell streak lines are, but you don't really fully understand that. Does anyone sort of, yeah.
So, like I get path lines and streamlines.
Yeah.
For streak lines.
Yeah.
What exactly is it measuring about that group of particles that are passing through the point?
Sure. Like when you say what is it measuring, like what can we get out of that, or do you mean like?
Well, you're saying it's the connected line of fluid particles through a particular point. But what is that connected line represent? Do you get what I'm saying?
No, I kind of see what you're saying. I mean, how would this, like, you imagine like a smokestack from like a power plant, like that is the streak line, right? There's a lot of different like particles in that like sort of smokestack, right? It's not just one particle which has been traced.
Mm-hmm.
There's a lot of, and so like that smokestack can be affected by like wind pushing it, whatever. There are like external like factors which are going to like affect like the streak line itself to move with time versus like the path line. Like once it finishes like a certain part of its path, like that's fixed.
Mm-hmm.
Like it can no longer like move or like change. Everything like before, like let's say there's time t equals like s. Let's just say time t equals s is like, I don't know, like right here or here, like time t equals s is like right there on the path line. Like everything before it like isn't gonna change, right? But like with the streak line, you can actually move with sort of like the acceleration of the flow. So like I think like a good way of looking at this is like, let's just imagine there's like a constant, I don't know, let's just say like hypothetically there's a constant velocity in the right direction, and then we're applying just like a wind or some sort of like other sort of like flow to the bottom. We can see that like that die is going to move like with time, like that whole like streak line is going to move with time.
Mm-hmm.
Does that sort of make sense?
Yeah.
Yeah?
Yeah.
Okay, cool. Definitely took me a lot longer than that to understand, so that's good. Cool. All right. Glad that we all on the same page there. All right, so this is another pretty basic fundamental concept that we got to understand. Like, what is the continuum hypothesis? So if we sort of like imagine that like on a molecular scale, like there's obviously like a lot of different movement going around like in like fluids, right? Like obviously in something like a gas, you're gonna have like a significant amount of movement, and like obviously like the movement can be denoted by like what the mean free path is of that particular molecule, and that can be in a gas a lot larger than in a liquid. What I mean by mean free path is basically like how much distance is the molecule going to take before it hits another molecule. So in a gas, like this is like a lot larger than in a liquid. But if we don't take things like at that molecular scale, if we sort of like expand a little bit larger, we sort of just assume that like we have like this sort of like box or like parcel, whatever, like it may be whatever shape that we want, that can contain enough of these like molecules, where essentially we can sort of like model this as like an element where we can say there's a consistent amount of consistent amount of variables, which sort of like represent this fluid element. So like it's like energy isn't changing a significant amount of time. Like there aren't like basically like if we take too small of an element, then there are going to be times when like particles are leaving, particles are coming in. There may be a lot of different variation in sort of like how much like mass is in this sort of like fluid element, et cetera, et cetera. But we sort of like want to imagine like this parcel of air to be like large enough where it can contain molecules to sort of like normalize all of those parameters, but small enough so that everything's like uniform without, so that we're not like imagining like a room, for example, where obviously we can have like different temperature gradients, et cetera, different, right? Different pressure gradients, whatever. Yeah. So now that we sort of like assume that we have like that parcel of air, we can sort of assume that like in a region, and we can say like any region, that this continuum hypothesis essentially states that there is no discontinuity with any sort of like one of these parameters that I mentioned, like pressure, temperature, density, et cetera, that every single fluid particle which is next to each other has like small enough of a change that like if you go one by one, you sort of like don't notice it at all. But like in the grand scheme of things, once we have like imagine like like an extremely small like change between each one that you're not able to even notice it, but like in the grand scheme of things, you can actually create like sort of like gradients and et cetera. But like a bunch of like partials there. Like you can imagine like in an integral, right, you have like your dx, sort of like this is our like dx, right? It's like our small enough sort of like element. Cool. And then another key point here, two main forces on these parcels and then on fluids in general, normal and shear forces. So that's pretty self-explanatory, but just to emphasize it a little bit more, normal forces are going to be like directing onto the surface, and then shear forces are along the sort of like sides and lengths of the surface itself. All right, cool. So in a solid, I mean, so the big thing between like a solid and fluid is that like when you apply shear stress to like this fluid element, like what is the discrepancy between those two? In a solid, once you apply like a certain force, it's going to deform a certain amount, but that's it, right? And that's denoted by like, so we can say like whatever our shear stress is going to be like the force that we apply over like that reference area, and the strain which results from it is going to be like that displacement in the direction of that force divided by some reference length, so h in this example. And like with a solid, when we deform that, it's going to stay at that certain length, and if we take off that force, it's going to deform back, right? And then obviously the amount that the stress is going to affect the strain is denoted by shear modulus. But in a fluid, it's a lot different, right? So when you apply that shear stress on your fluid element, you're going to have instead like the fluid is going to keep on deforming, and we can basically say that that strain rate, the rate at which like essentially that sort of this fluid parcel is like changing or deforming, is like this strain rate, right? So like, so it's basically that, so it's like basically denoted by like that length divided by time there. Cool. And yeah, and we can denote what our shear stress in a fluid is by like this new term, viscosity. So basically like the more viscosity you have, the less of a strain rate you're going to have with a given shear stress, right? So that's pretty intuitive to understand, right? Like the more viscous your fluid is, the more amount of the same amount of shear stress that you're going to have, the less it's going to be deforming and having like that strain rate. Like think like of honey or whatever compared to gas. And this is kind of interesting. You can sort of like derive like where Reynolds number comes from, and before we even get into Reynolds number, let's just go back to what we're trying to do here is sort of like compare So we basically had like two main forces that we specified earlier, right? The normal forces and the shear forces. We sort of like create a ratio between those two. We just say that like a normal force is going to be caused by some sort of pressure variation, some delta P, and we can say that our shear force is going to be caused, by like a shear force. And we sort of just basically say that given like that formula that I showed earlier, our shear force being that viscosity multiplied by our strain rate, if we just like decompose like what sort of like variables we're seeing like a speed and a distance, right? So like the speed and a distance denoted by like U and L respectively. Now we do like the same sort of like kind of dimensional analysis with a change in pressure. I mean, this is just an example like rho GH. Obviously, like rho GH, like density times gravity times height, isn't going to be like very useful in a lot of our cases, but the units are consistent throughout like any type of pressure, and we could just see like what sort of like units are present in that formula, and we sort of like rearrange to get like a density kilograms per meter cubed and a speed squared. So we can basically just like say that this pressure variation is going to be scaling with like those two units, and then we can basically just go back to our previous like sort of relationship between like a pressure force and a shear force, and then we can sort of like combine these two and say that we basically just get Reynolds number right there, which is another way of putting it is a relationship between the inertial forces of a fluid and the viscous forces of a fluid. They're a big sort of like follow that. It's like some pseudo derivation that like my freshman aerospace engineering teacher showed me, but it seems like pretty cool. Everybody on page there? Awesome. So yeah, so Reynolds number is like going to be a very important sort of like concept, obviously, with fluids, because we want to be able to like identify like how much our flow is being affected by inertial forces, how much it's being affected by viscous forces, because that affects a lot of different things. Turbulence is one in particular, but before I get into that real quick, you can sort of see like at the bottom picture right here, at low Reynolds numbers, like in this case lower than 5, which is sort of like called creeping flow, because the flow is like just creeping along like the body. We can see like how much that varies along like a cylinder in this case, if there's just free stream coming from the left, to much higher Reynolds number, where there's like a lot more separation going on, and there's a lot of different like regimes of Reynolds number which are going to affect like the different characteristics of your flow, and in particular, for example, for external flow, a key number to note is 500,000. So that's like sort of like the transition period to turbulence. So like what is turbulence? Let's talk about that a little bit. It's basically like, if you think about like what regular controlled like flow would be, like everything is very uniform. That's sort of like what laminar flow is. Turbulent flow is going to be a lot more disorganized, but it's also going to have like a lot higher energy. Like if we have like the same like average velocity towards the right there in both these cases, because there's a lot, obviously, like a lot more components of velocity within like all this. But yes, like I said, so the transition period between like laminar and turbulent flow is usually happens around like 500,000 Reynolds number. So we could sort of like apply that to a lot of different things. So if we like calculate a Reynolds number of like a wing, for example, we can sort of specify like, oh, is this going to be primarily in like laminar flow? Is this going to be primarily in turbulent flow? And there's a lot of different things that we can like sort of like get from there with approximations of drag, approximations of boundary layers, so on and so forth. And I said like 500,000 for external flow, and then internal flow is like about 2,300. And this is another very important concept, boundary layer. So essentially what we have to sort of like understand here is what our velocity profile is doing with respect to like distance away from the surface of an object. So like if we have like a flat plate, which is the general sort of like idea, everything is a flat plate. If we have like a flat plate moving along or like free stream air moving along a flat plate, something called the no-slip condition is going to specify that at the surface of the object, there's going to be velocity. The velocity of that of the flow is going to be 0 because of like friction effects with like the actual object, because of viscous and frictional effects with the object. In an inviscid case, this wouldn't happen. But every like in reality, there is like viscous forces, and this is what actually happens at a boundary. So if we basically plot like velocity, its magnitude as a function of like the distance away from the surface of an object, our boundary layer thickness is essentially envelopes every velocity which is lower than free stream. So anything outside of the boundary layer is going to be free stream flow, and anything inside of the boundary layer is going to be some velocity less than that. And the general profile that it takes is sort of like this, sort of this shape, this curved shape that you see here. But yeah. Anything else? And there's like different sort of like equations that we can use to model boundary layers. There's like the Blasius equation and whatnot, which uses basically empirical data. And this is going to be affected a lot by Reynolds number. Yeah. And whether or not, by Reynolds number, and then whether or not the flow is turbulent. So those like empirical relationships, which I was talking about earlier, are going to be different depending on if the flow is laminar or turbulent. Okay, cool. So now getting into sort of like forces and on an actual object. So the two main forces, or the two main effects on airflow on the surface of an aerodynamic object are going to be the pressure distribution on its surface. So you can see like from that picture on top there, and then shear stresses on the actual surface because of that boundary layer. That boundary layer is basically creating friction on the actual aerodynamic object. And we can sort of like use these two to develop overall aerodynamic forces of the entire object. So if we basically we can basically integrate over the entire like surface with pressure with respect to like its area, and then that gives us like the aerodynamic force in whatever direction it may be. And then similar thing with the shear stress, except that's going to be only in line with the actual surface that it's acting on there. But yeah, so that's pretty basic stuff. Right, cool. So one key point here is that as our velocity is going to be increasing, the boundary layer size is decreasing because there's more of like inertial effects essentially, which are taking over there rather than viscous effects. Right, so going back to our Reynolds number equation, being the relationship between inertial and viscous forces, what was in the numerator, the inertial forces encapsulate velocity. So as like those inertial forces are being more predominant in our flow, the viscous effects are going to be lessened and lessened. Our boundary layer is going to decrease, and the skin friction is going to decrease. So this has nothing to do with like the actual pressure drag, which is going to actually increase with speed. But if we just look at skin friction itself, we can see that as our velocity increases and which correlates with Reynolds number, our skin friction coefficient is going to decrease. And then there's this transition point, which I mentioned earlier, like 500,000 on a flat plate with external flow, where we go to like a turbulent boundary layer. But something interesting here to note is that at low Reynolds numbers, our laminar boundary layer, at lower Reynolds numbers, our laminar boundary layer, at lower Reynolds numbers, our laminar boundary layer has less drag coefficient than our turbulent boundary layer. But as you go higher and higher, our turbulent boundary layer actually has lower skin friction coefficient than our laminar, because again, like those inertial forces are sort of taking over. And another key point here is how turbulent boundary layers can affect flow around a body. Because it, like I said before, it has more kinetic energy, we can actually delay the flow separation on a particular object. So, for example, like if you trip the flow, and like you have an intentional boundary layer trip, for example, then you can actually potentially go to higher and higher angles of attack, and I'll get into that a little bit later, without compromising your lift and stalling. But then, so is stall? Basically, we have to understand what is an adverse pressure gradient first. And this is a pretty key concept as well. But basically, on the left, we have like the pressure distribution on the airfoil. And then I just want to point out here that there's a negative pressure on the top surface here and a positive pressure on the bottom surface. What? That's weird. Yeah. There's the amount of there's negative pressure on the top here and the positive pressure on the bottom. But the magnitude of pressure as you're going right on this top surface here is decreasing. But because it's negative, the pressure is actually increasing, right? Does everyone understand that? Basically, like at that point here at S2, we have the lowest pressure on our airfoil. But at the trailing edge, we have atmospheric pressure, right? Because the flow has to rejoin with atmospheric pressure. Okay? So essentially, like if we have a low pressure region over here and a high pressure region over here, then what is the flow going to want to do? It's always going to want to move from high pressure to lower pressure. And the key point here is that if our adverse pressure gradient is too strong, what essentially happens is if we go to our boundary layer, we can see that as we move further and further along the length of the airfoil, because of this adverse pressure gradient, which is pushing, we're sort of like creating a pressure gradient backwards, at some point, we actually have flow in our boundary layer going the opposite direction. So this is literally going like the direction of like free stream flow in that location there. And like what does that create? That creates like an eddy or a vortex like right there. And this essential that sort of like redirection of flow there is what flow separation is like at its core. Right? So like if we're sort of like create too much of a low pressure region that our adverse pressure gradient is too strong, we're going to inherently have some sort of flow separation. So that's sort of like the fundamental reason like why there is flow separation to begin with. We sort of get like this boundary layer, which is literally like having flow go in the opposite direction, which is so weird to think about, but that's what happens.
So does like the pressure gradient and the flow kind of impact each other? Because I was just thinking about why is there lower pressure at S2 compared to the edge of the airfoil?
Yeah. So the shape of the airfoil sort of like affects the direction and velocity of the flow, which inherently is related to the pressures at that particular region. So like for example, and I'll get into this on this slide right here. So like as if we imagine like a stream like tube, right? A stream tube which is essentially like no flow can go in or outside of its boundaries. Okay. We can basically say that mass is going to be conserved within this case, and then energy is going to be conserved. And the two sort of equations that derive from those relationships or from those principles are the continuity equation from mass being conserved and the Bernoulli's equation from energy being conserved. So, like, from your question, because like the airfoil is sort of like affecting the flow velocity and the flow direction, it affects inherently the pressure at that particular region, creates like this sort of pressure gradient on the airfoil. Sort of makes sense?
Yeah.
So yeah, right. So like as velocity is going to be increasing, our our pressure is going to be decreasing. So like correlating back to like the airfoil, like at that extreme low pressure region here, the velocity is at its peak. So yeah, like I said, yeah, the total pressure is conserved in that streamline for that stream tube. And this relationship we can utilize to do a lot of different things, but primarily basically figure out like what velocity is at a particular region. We can basically get the velocity in free stream conditions from something called a pitot tube, which essentially isolates the static pressure component and the dynamic pressure component. So if we basically imagine there is no like movement in the flow whatsoever, we're gonna have no velocity, then that is our static pressure, so like the ambient pressure, which is gonna be existing. But how do you sort of like measure that on a moving object? That's like where the pitot tube sort of comes into play. Basically, the flow is moving. Basically, there's two ports on the pitot tube. The flow that is sort of going directly into that nozzle there, which is creating a stagnation pressure, which is that stagnation pressure is the total pressure in that case, which encompasses both the static and dynamic pressures, and then we can measure just static pressure from these sort of like yellow ports on the pitot tube, which sort of just are normal to the direction of the flow itself, which don't sort of like take in any of that stagnation or dynamic pressure, because it's not based. If you just imagine like the flow is being like forced into that tube, creating like a stagnation effect, as compared to like those ports which are just normal to the actual direction of the flow. And then using that, we can basically like calculate velocity, because if we have our stagnation pressure, which in this case is our total pressure, and then we have our static pressure, then we can just subtract the static pressure from the stagnation pressure to get our dynamic pressure. And then knowing density, we can get our actual velocity of the flow. And using dynamic pressure is pretty important in fluids as well. So that 1/2 rho u squared, it's utilized to normalize a lot of different coefficients. So the main one being like force coefficients, like lift coefficients, drag coefficients. You'll see that like we have the force divided by some reference area multiplied by the dynamic pressure, because that's sort of like how we can compare like apples to apples, and be able to basically say like what would the forces or whatever pressures, skin friction be if we sort of like modify this velocity parameter. But yeah, so we can derive a pressure coefficient, a skin friction coefficient, and like I said, the force coefficients. So the pressure coefficients, basically like we can take the differential between like the pressure that we're measuring from like a tap, for example, and then with atmospheric or static pressure, and then divide that by dynamic pressure to get a pressure coefficient. Skin friction coefficient, similar thing. Basically, your skin friction value, which is tau, which is a force, and then that divided by dynamic pressure, and then like I said before, with force coefficients like drag coefficient and lift coefficient or downforce coefficient, and then just a quick sort of note here between skin friction coefficient and drag coefficient. So like I said, there's like pressure effects on drag, and then there's skin friction effects on drag. So that sort of just like creates that discrepancy there. And we actually use a pitot tube on our car to measure velocity, so I think that's pretty cool. And so do like a lot of F1 teams and some other applications for this can be like, for example, creating a pressure rake. So you can see this a lot in F1, and we use this as well. We've been using it on our radiator, sort of like create a a lot of different ports which we can measure are that stagnation pressure that I was talking about, and then you can isolate what that velocity is going to be at that particular point. And then using that velocity, sort of like basically take like, in the case of the radiator, you can take like an average of that multiplied by the area, and you can get like a mass flow rate that way. So pretty applicable stuff. Right, so now we see how we're doing on time. Oh, did not expect that. All right, so yeah, so try to speed it up a little bit. But yeah, so what is an airfoil? So we talked about this a little bit before, but basically the point of it is to redirect flow velocity field, which, like I said, creates that pressure distribution from like that conservation of energy equation that I was talking about before. And then some key things to know here with the case of an airfoil, or in this plot, like free stream velocity, your wing. So airfoil is the 2D profile of your wing, essentially. Okay, that's like the terminology that's generally used. So you can see like the airfoil being shaded in gray there, because like that airfoil shape can change like along the span of a wing, and frequently does in the case of like an aircraft wing or like an F1 wing, etc. And so another point, another term here is angle of attack, denoted by alpha. Basically, that's the if you have a line connecting the leading edge to the trailing edge of an airfoil, that the sort of like angle that line makes with like free stream flow, that's your angle of attack. Cool, yeah, and then so that from the redirection of flow, we can sort of like create a pressure distribution, and like this is like an example of pressure distribution that you see here. You can see like in the case here with this airfoil that the amount of contribution from the top side is actually towards lift is a lot more than the bottom side, and obviously in our wings, which are inverted, it's the flip side. So the bottom surface of our wings contribute a lot more to the downforce creation than the top side of our airfoils. Yeah, and this is just like a sort of example of what you could sort of like look up for different types of airfoils to sort of see like what the pressure gradient or pressure distribution is of that airfoil at a particular angle attack. And there are different softwares that we can use, like CFD, Xfoil is another simulator which essentially uses some panel codes to sort of like predict what that two-dimensional airfoil, what its performance is going to be, and like what its pressure distribution is going to be. But yeah, so we can basically like integrate this and actually create sort of like lift value. Another couple of terms, so chord length, thickness, and camber. So chord length is just the leading edge to trailing edge distance. Thickness is just the top to bottom thickness of the airfoil, and then camber is how much it's sort of like curved. It's usually sort of like measured as a function of chord length. So you could sort of like see camber be denoted as a percentage, and that basically means like how much your max camber point, like that max point which is deviating from that center line, how much is that moving away from its original point using chord length as a normalizer. So if you see like something like 5% camber, so you can say that means that the sort of like amount that the section, that middle point of the airfoil, which is sort of like pulled up the most, is like 5% of the chord length above like the midpoint of that equivalent symmetric airfoil. Yeah. So why do we add camber? Yeah, it basically sort of like helps to better redirect flow. Basically, what the air wants to do is sort of align itself with the airfoil. So if you already sort of like have this leading edge of the airfoil sort of like shaped to be aligned with the free stream flow, or if you have it aligned sort of like negative or like below the free stream flow, like the air is going to redirect itself to the stagnation point of the airfoil, so creating basically more redirection of flow overall. So if you imagine like what is actually like causing lift to begin with, I talk about like these pressure gradients, but if you just imagine like from a fundamental sort of idea like every force has an equal and opposite reaction, you sort of imagine like if flow is being directed downwards, there has to be some sort of force like pushing the airfoil upwards. If we're sort of like introducing more of like this curve such that air is forced to start sort of like from the bottom here and then end up directed downwards here, the net amount of sort of like redirection of flow is like this whole distance here, right? So it's a lot more compared to just like a symmetric airfoil, which may start like this, which free stream air may start like this and then be redirected downwards. Does that make sense? There's sort of like a hand wavy explanation there, but I think it does the job. But yeah, so you can basically like I pointed out before, we can sort of like add these pressure distributions. So like if we have like a cambered airfoil, we can split it up into like what its symmetric components are going to be and what its like camber effects are going to be, and we basically like add these two together to get an overall third pressure distribution, which is pretty cool. I talked about this already, but yeah. So generally speaking, like your force is going to be divided by your dynamic pressure times the reference area. Dynamic pressure denoted by Q, and then your reference area is going to change depending on like what sort of like object you're looking at. For a wing, it's going to be like the planform area of the wing. For like a car, it's going to be the frontal area of the car. All right, so speed right through this. So the effect of our angle of attack, it's going to have a linear relationship. Generally speaking, this is pretty cool, but a 2D airfoil, its lift slope. So basically, like the amount that its lift coefficient is going to change with respect to angle of attack is exactly 2 pi. And you basically multiply like 2 pi multiplied by like whatever your angle of attack is, and you can get like what its lift coefficient should be. This is the two-dimensional case. And essentially, we can compare a cambered airfoil and a symmetric airfoil here, and we can see that it's actually not changing the slope of this curve. So like as angle of attack increases, the amount that you're increasing lift coefficient isn't changing between a symmetric and a cambered airfoil. But what is changing is at your zero angle of attack, you already have lift with your cambered airfoil. Or conversely, you can think of it as at a negative angle of attack is where you have zero lift on your cambered airfoil. So you're basically just shifting over that curve. Another important point, this is how thickness affects our airfoil. Thickness affects our lift curve slope, lift angle of attack slope. It doesn't affect the slope, but it essentially we're able to extract more lift coefficient out of it before like this wing actually stalls and has like that adverse pressure gradient, which is too strong, which creates flow separation. Basically, like that sort of dip that you see over there is like what stall is called. It's basically like a reduction in the actual overall lift that is being generated by this wing or this airfoil after a certain point. Because like as I said before, like once your adverse pressure gradient gets too strong, you have flow separation, and once you start to have flow separation, the amount of force that's generated by that wing is going to be a lot less than prior. So we have like a couple of different thicknesses there. So like as thickness is increasing, so you get like higher numbers in the NACA series, you can have higher lift coefficients and higher stall angles. So we sort of talked about this already, but there are two kind of different sort of types of stall which is pretty important. There's like this sort of like gradual stall, which you sort of see here, and a more abrupt stall, and you can even see that in like these examples here, like the thinner airfoil, the thinner NACA airfoil had like a sort of more gradual stall compared to a more sharper stall, and you can kind of like see why there might be like more importance to have like something like that in the case of a race car where you don't necessarily want the wing to suddenly like change the amount of force that it's generating after a certain angle, which is the case in the abrupt stall situation. But some like pretty key parameters which affect whether or not you're going to have gradual or abrupt stall is the shape of the leading edge. So like the sharper the leading edge is going to be, the more chance you're going to have abrupt stall. And the reason for that is the separation that's going to occur is going to happen a lot closer to the leading edge of that airfoil. Because it has to basically, the air has to basically redirect itself a significant amount over like this corner, which it doesn't want to do because it has like that inertia which it already has, right? So it already has like that significant amount of inertia. But as Reynolds number is less, where you have more viscous effects, you may be able to sort of redirect and go around like that corner a lot better. Like you kind of see in like that cylindrical flow example from way back before with creeping flow, it sort of basically follows the profile of like that cylinder perfectly. But like in our more like useful cases, in our higher Reynolds number situations, you want to make sure that like your leading edge is shaped very well and is very round. And so yeah, so thicker, highly cambered airfoils, you're going to have like more of a gradual separation. So now this is the more interesting stuff. So what happens at wingtip? So before we were just talking about airfoils, like 2D profiles, which only sort of like take into account, which basically imagine like an infinite wing. But if you have like a finite wing, what's going to happen at your wingtips? You just like kind of like do a thought experiment here. We already specified that one side of the wing is going to have a higher pressure than the other side of the wing. And like I said before, flow wants to move in the direction of that pressure gradient. So we have like a pressure gradient in this case. In this wing, which is cambered in this way, we have lift in the vertical direction. So we have a negative pressure on the top, a positive pressure on the bottom. And that pressure, that air is going to want to spill over essentially from the high pressure to the low pressure region. You can kind of see like as the wing is moving with air, or like it doesn't matter what reference frame you're in, but in free stream air, as that air is sort of spilling over the side and moving backwards, it sort of like creates like this vortex, or like this spinning sort of vortex at the wingtip from this spillage effect. And we can actually have an empirical sort of equation here to get our relationship between our finite wing lift coefficient slope and our infinite wing lift coefficient slope. So if our infinite wing lift coefficient slope is always going to be 2 pi, then all we need to know is the finite wing's aspect ratio and its Oswald efficiency. So aspect ratio is basically this sort of the relationship between a wing span and its chord. So the more slender or long the wing is, the higher its aspect ratio. And you can see from this equation that like as aspect ratio is increasing, that term on the bottom right there becomes smaller, so the denominator becomes smaller. The overall lift coefficient slope of the finite wing is getting bigger. So why is that? Like, why is a long and skinny slender wing like more effective? And if you again think about like what these wing vortices are sort of doing, it's basically reducing the span of the wing. It's reducing the effective amount of surface area that you have to generate lift. So like as you get like more stubby and stubby and stubby, the amount of surface area that is basically being taken away from by these vortices basically envelops like the whole wing, right? So like as we and the flip case, like if we have a very long and slender wing, the amount of span that is being reduced proportional to like the overall like amount of lift generated by that wing is going to be a lot less. So that's why like gliders have super high aspect ratios and whatnot. But yeah, so this is a pretty cool equation that sort of like used to sort of identify what a finite wing performance is going to be. And then Oswald efficiency is basically like dependent on the geometric shape of the wing. Elliptic wings have an Oswald efficiency of 1, and then there are different shapes that have different efficiency factors. But generally speaking, they're in between like 0.9 and 1. Cool. And then, so because of like that Horsey effect, we also have an induced drag effect, and that scales with the lift coefficient squared. And that's very important because what that means is that like as we double our lift, we actually increase our induced drag by 4. So it becomes like a lot more impactful as you keep on increasing your lift. And then you think about it even more. But yeah, that's what I want to say there. And then another thing about drag. So I just introduced like this new drag component, like this induced drag component, but that combined with the drag that I was talking about earlier from pressure and skin friction can be denoted by CD naught or just parasitic drag. That should be, CD naught should be like parasitic and profile drag in that case. And then induced drag is the other component to the typo there. But yeah, so this is also pretty cool, but so like I was saying earlier, there's a certain point at which your angle of attack is going to get too great, and your wing is going to stall. But if you keep on adding wings together and together, you can sort of like create like this multi-airfoil, multi-element wing. In this case, the theoretical limit is 42 degrees. But you can sort of like see like the overall airfoil shape there, which is encompassing like these smaller wing elements. But basically the point here is that it's sort of twofold, but essentially the main point here is that if we just imagine 2 airfoils, we want to create a suction point at the trailing edge of the first airfoil. Okay? And the way that we can do that is by sticking another airfoil where its lowest pressure point is right by the trailing edge of the first airfoil. So you can see like in those pressure distribution plots that I was showing earlier, generally speaking, our like lowest pressure region on our airfoil is going to be like at like the top point of like the camber that we have. And you can see that in this case, that second airfoil is placed just where that low pressure region is maximized on that airfoil at the trailing edge point there. And so why do we want that to happen? This basically allows us to increase the magnitude of low pressure on our first wing because now we can deal with a larger adverse pressure gradient. Or from the flip side, we deal with the same adverse pressure gradient, but our trailing edge is no longer at atmospheric pressure. It's at this lower pressure than atmospheric pressure than before, right? So does that sort of make sense to everybody? But that's a pretty cool application there. And you can see like in airplane wings and whatnot, there's a lot of different like slats and slots and whatever. And even on our car, we have like 3-element front wing, 3-element rear wing, etc. But another thing here is that with that slot, we could sort of like introduce higher energy flow directly to the latter portions of our secondary element, and that's sort of like the second beneficial point there. So like even though like our last airfoil may be like at 42 degrees, which is like never possible with an actual real wing on its own. It can be accomplished with in combination with a lot of other elements, because the effective sort of like free stream flow that it sees is a lot more angled than the overall what free stream flow is in reality, right? Does that sort of make sense? Like the free stream flow, like the eighth airfoil here sees is like in this direction already, versus like the free stream airflow that the first airfoil sees is in this direction. But yeah, you can see that like we can get like some absurd lift coefficients here, like 3.5 with like, what is it? Yeah, or some crazy numbers like that with like a bunch of different wings put together. Cool. And then so to prevent our vortices, to sort of like block them, we can do something add end plates, which is pretty common in a lot of different applications. And we can sort of like have this equation to sort of see how our effective aspect ratio of our wing is relative to the actual aspect ratio of the wing with the addition of this end plate, right? So like with the, we can sort of like see like the height, the relation, we can sort of like get this parameter, these two, this number to the right here from the addition of end plates. And we can actually increase our effective aspect ratio of the wing, which is pretty cool, right? Because like, as I said before, our actual lift coefficient slope is going to be directly linearly, or not directly linearly, but is going to be related to or positively affected by a positive increase in aspect ratio. Cool. And then so touching up on vortices some more, this is sort of like where ground effect comes into play. Like, why does putting a wing closer to the ground actually make it perform better? The reason being that you're sort of basically squishing or like pushing these vortices to be a lot smaller than they otherwise would be, because they can't go anywhere, right? They touch the ground and that's it, right? Or like they move outwards. So you're basically shrinking the the overall size of these vortices, and you can see like as we are basically decreasing the distance of the airfoil to the ground, we're increasing our two-dimensional lift curve slope here. And the person who made this plot definitely made a typo, because if the aspect ratio is an infinite, ground effect shouldn't affect the lift curve slope here significantly. Cool. And then the same thing happens with like on your underbody, like on an under tray, for example. So you sort of see like our peak lift coefficient is going to be like a lot closer to the ground than it would otherwise. Than it would be like a lot farther from the ground, because of the same reason there. But I mean, also there's another point there, because like you're sort of like basically, in the case of the underbody, you're sort of basically like trapping the flow in that case, sort of creating a closed region, and then going back to Bernoulli's principle, conservation of energy, you have to like, because you have a like closed region where like pressure or energy has to be conserved, there's going to be less basically spillage of air outside, and from that we're going to be able to maintain a much lower pressure at the inside the underbody there than we would otherwise. So there's a little bit twofold there in the case of the underbody. But on the wing, in the wing case, it's pretty much just like the squashing of like these vortices, these wingtip vortices. And then some more devices that we can use. Some other devices we can use. So I mentioned a boundary layer trip before. So that can basically just be like a rectangular strip. But if you want to be a little more precise with what we're doing here, to sort of like energize the boundary layer, we can sort of introduce these different types of vortex generators, and here are some examples of some. And this is actually pretty interesting here in A, if y'all can see that. But that's basically just like a tiny airfoil perpendicular to the surface there, because you're using those vortices that we were talking about earlier from like a finite wing, and you're creating a vortex exactly where you want it to be, essentially, and you're introducing energy like in a very controlled manner that way into your boundary layer. So that's an interesting sort of like vortex generator there. But the other vortex generators are doing the same thing. Essentially, they're creating vortices in the direction of the flow, so that we can increase the amount of energy in the boundary layer, and then effectively from there we can the more energy that we're going to have in our boundary layer, we can have like stronger adverse pressure gradients, and we can prevent flow separation that way. Cool. So now moving into like how we're actually affecting aerodynamic performance, how we're actually affecting vehicle performance with the vehicle performance.
We did this last week.
Okay. All right. I'll just go over this pretty quickly, but yeah. So the three main forces on a tire, like FC, FY, FX, according to like a Cartesian coordinate system. But we could basically just say that like if we have some sort of slip angle, a change in direction from like the heading of the tire versus like the versus the direction the tire is actually going, which is noted by beta here, that can create a lateral force, which is basically like what actually creates steering, the ability to go around a corner, and basically there's like this linear range or linear region where up until a certain point, up until a certain slip angle, you can basically increase or extract out a higher lateral adhesion coefficient, which is the relationship between the lateral force and the normal force on the tire, up until a certain point at which like you basically slide. And then going a little bit further, with a higher normal force, we can extract a higher lateral force out of the tire as well. And the same thing, like there's going to be a linear range there up until the point, and then you start to slide, and the car becomes uncontrollable at that point. And then like from there, if you combine like both longitudinal and lateral forces, you can sort of like get this idea of a grip circle, where you can basically plot the amount in G's that the vehicle can take before it starts to slide, and you can plot this as a circle, or it's not always usually a circle. Sometimes it's like some sort of like oval, but essentially like you can see the effect of longitudinal performance and lateral performance of the vehicle. And like as you add like more downforce, more normal load to that, you basically expand the circle. And basically there's the impact on lap time. So as you're cornering around like a particular circuit, like increased downforce is going to decrease your lap time up until a certain point. You can see like this sort of region here. This is just an example. Up until a certain point at which your lap time actually does increase because drag effects become significant. Because at some point you're going to be power limited, right? So if you imagine like power of the vehicle like needed due to drag, that's going to be like your drag multiplied by your velocity, and your drag has what in it? It has a velocity squared in it. So the power required due to drag is actually going to correlate with v cubed, with your velocity cubed. But in cars like ours, we don't really care about it too much because we have a lot of horsepower compared to like the amount of weight that our cars is. But yeah, so this is just like a simple example that I just made in MATLAB. Very simple assumptions. Like if basically we were just to assume that the centripetal force of the car was equal to the lateral grip, and if we just like imagine just everything else was constant, like weight, etc., downforce coefficient, everything, constant grip coefficient, whatever. We can see sort of like how, and these are using parameters like from our car, like the weight of our car, our downforce coefficients, everything here. We can sort of see like the effect of that downforce has like with our full air package on like a particular corner. Cornering radius. So like as like radius is increasing, we can see that the divergence between not having arrow and like with arrow is going to become larger and larger. And you can see like the time discrepancy there with different radii and the corresponding velocity discrepancy as well. But going a little more fidelity, you can use like optimal lap. That was just like a simple sort of like model that I made in MATLAB, but you're sort of like you can put a lot of more different parameters like engine performance, like our torque curve in our engine, input like the shifting bands, etc. We could sort of basically see like how a combination of drag and downforce coefficient can affect our lap time. I made the axes here a lot larger than they should be on purpose. This is using parameters from our car, STR23, but our drag coefficient isn't nearly like this high. It's like about like what was it, about 1.9. No, it's like about like 1.2 or something, 1.3. But basically what we can get from this is that we are definitely not power limited at our current state. There's a lot more elements that can be added to the car to increase downforce and also increase drag while still decreasing lap time, essentially is what I'm saying. Like up until the point where like you sort of get this drag divergence and like you don't have enough horsepower due to drag from power needed for drag, which seems to be like, I don't know, around like 1.7-ish about in this model. But yeah, so definitely have a lot more to go. But essentially like we can sort of like see what the effects of like these two coefficients are on like lap time, right? So like as drag coefficient increases, we're gonna have slower lap times. As downforce coefficient increases, we're gonna have faster lap times, right? But finding that like combination, that sweet spot, is sort of like why you use like these models. Yeah, this is another example here that sort of like justified the use of the vehicle under tray. You can see like without arrow where we are, with the front wing and the rear wing where we are, and then like with an under tray like where we are. And this is on Lincoln Endurance 2019. And oh yeah, this is another example of that, but similar concept really. Cool. And then another important concept here is center of pressure. So those models that I showed before are point mass models, so they don't actually account for the suspension changing heights in the front or rear. But those effects are very important, actually. And the reason being because, like I said before, or like I showed before, a wing in ground effect, as it moves closer and closer to the ground, is going to have more downforce generated up until a certain point. And same thing with like underbody, right? So the effects that the suspension depressing has on aerodynamics is significant, and the effect that it has, like for example,
what do you want to say?
Under pitch, are going to be significant. Under like under squat are going to be dive and squat are going to be significant because in both cases now, because we have an under tray. Previously we didn't, so it was more like dive that we were concerned with. But yeah, so the idea of like a center of pressure, like a downforce center of pressure, is basically like if you imagine correlated to like the center of gravity, right? So like center of gravity is like if you imagine like all the weight is concentrated in one point. That's like sort of like you can use that in solid body models. So same thing with the center of pressure. You basically imagine all of you're integrating all of your force, and you're saying that it acts on one point. So what basically this means is that if my center of pressure, my downforce center of pressure is, for example, forwards of my center of gravity, that means that there is more downforce forwards of my center of gravity than there is aft of my center of gravity, right? So usually the way it's measured is in something called aerobalance percentage, percent aerobalance, which basically is the percent of wheelbase. So wheelbase being like the distance between the front and rear tires, the percent wheelbase ahead of the rear axle. Okay, so let me know if I should draw that out. But essentially, so 50% aerobalance would be halfway between the front and rear axles, because that is half of the distance, half of the wheelbase in front of the rear axle. So 100% aerobalance would be like at the front axle, 0% aerobalance would be at the rear axle. I think that's pretty much like is a good explanation there. But yeah, so you can basically see this is another plot of our car. We can sort of see like how our center of pressure is affected. Our downforce center of pressure is affected by varying front ride heights and varying rear ride heights. So you can see like as we're going leftwards here, so our rear ride height is decreasing. See a general increase in a general like moving backwards of our downforce center of pressure, right? So like as the rear ride height decreases, our undertray is getting closer to the ground. It's becoming more effective because of ground effect, and the downforce center of pressure is therefore shifted backwards. You can see like, so if we just pick this point right here, as we're going left and left, the downforce center of pressure percent front is decreasing, becoming darker blue, and then flip on the front side. What we can see from this plot that the effect that the front ride height has is a lot more significant than the rear ride height. So, yep, that's pretty interesting. Cool. And then so the corollary to that in the other direction, in yaw versus, or in lateral direction versus the vertical direction, is the side force center of pressure. This is another pretty important center of pressure that isn't always looked at in race car development, but it is also pretty important because it's the same concept, right? So imagine all the side force on our car is being acted at a particular point, denoted by like that side force center of pressure. Its location relative to the CG is going to have an impact or some sort of moment, right? Because let's say that our center of pressure, let's say that there's some like free stream airflow coming in this direction. The car has some sort of aerodynamic yaw. If our center of pressure is behind our center of gravity, which is generally at center wheelbase, because that's how the BD team tunes it to be on the scales. It's generally going to be 50% in front of the rear axle. So if it is essentially behind that CG or behind that center wheelbase, it's going to create some sort of corrective yaw moments, right? So we can imagine like you can sort of like imagine like if like I have like my center of gravity like at the center point here, if my center of pressure is like back here, like as all my forces are acting like here, it's going to like create a restoring force back to like that original position. In the same way, like that way, right? versus like if my center of pressure is in front, right? Then like as I have like some sort of like angle there, it's going to like create a anti-corrective moment. So it just depends on like what the driver is for.
What are like the magnitude of this force is, like the side force?
Like in terms of
It's like pounds force or something like that. Or like, I guess it's a moment, but like
Yeah.
so it's sort of, yeah.
I think like at max yaw it's something like 20-30 pounds on the rear wing end plates. But you get an actual moment value itself, like multiplied by the moment arm there, it might be a little more significant.
Because this is even compounded by having your downforce center of pressure behind your CG, creating more normal load on the tires, will
Exactly.
create like a really significant yaw moment. So yes, that kind of two things acting.
Exactly. There's two things acting, not just the downforce center of pressure. But yeah, we should definitely get a.
If we have a map for it, that would be
We do have the values. We just don't have it plotted. But yeah, getting a yaw moment versus yaw angle would also be helpful, which we should definitely do. But yeah, cool. And so like both of those points, which Lucas said, are going to affect over understeer. Having more grip on your front tires are going to have you're going to have oversteer because you're essentially you have more steerability. There's normal load on your front tires. Those are the tires that are actually experiencing larger lateral forces to create a turn. So you're going to have larger. You're going to have oversteer in that case, and then vice versa, like more downforce on your rear tires. You can have more of an understeering effect. Not that just because you have like downforce center of pressure frontwards of your CG, you're going to have oversteer. Obviously that's not the case, but it does impact like overall like how much steerability the car does have. And then these values are constantly transient in a corner, which makes it even more painful to deal with. Like I showed before, our downforce center of pressure, like with our ride heights, are constantly changing, and obviously in a corner, you're braking into it, you're accelerating out of it, like you're having dive into it, you're squatting out of it, like it's in around the corner, you're constantly changing. The situation is constantly transient, so it makes it even more of a pain to deal with. But yeah, and that is my intro lecture.
I would actually be really curious to do like a bicycle model, like skid pad simulation with and without aero, and like considering we could like totally calculate the like understeer gradient like with or without aero, like that would be kind of cool.
We should do that.
Yeah.
We should definitely do that.
Tomorrow we're really talking about bicycle